Welcome to The Math Show with Mr. DeClerico. So you're playing a game of Candy World with your friends, a game in which good things happen when you roll high numbers. You roll a fair six-sided die and you get a 2. And then you roll a 1, and then you roll another 1. You're mad, and understandably so. Your friends are already in Rock Candy Canyon and you're stuck in the chocolate swamp. Big time bummer. Your friend, who doesn't really feel bad for you, nonetheless offers a word of encouragement. You're due for a 6, he says. You consider. The odds of rolling a 6 are 1 out of 6, so in however many rolls I get in this silly game, 1 in 6 are going to be 6s. So I guess all my 6s are going to happen later to make up for their lack in the beginning of the game. You crack a smile. It's going to be okay. Except that your conclusion is completely wrong. You have fallen for the gambler's fallacy. So why is this manner of thinking wrong? Well, first we need to understand what we mean by the word odds. What even is probability? Most folks go in with the assumption that the probability of our event is the number of desirable outcomes over the total number of possible outcomes, which is not a bad instinct. So the odds of rolling a 6 are 1 out of 6. There are 6 faces of the die, they're all equally likely to be rolled, and we're looking to roll one number in particular, namely 6. But how do we know that's how it works? Here comes the monkey wrench. I could roll a die 10 times and conceivably roll only one 6. Does that mean the probability is really 1 out of 10? Yes. Well, sort of. There are two kinds of probability we're seeing here, observed and theoretical. Those 1 in 10 odds are the observed probability of rolling a 6 in the aforementioned 10 rolls. The 1 out of 6 then is what we call the theoretical probability of rolling a 6, or the probability that arises not from observing trials, but by using a mathematical model like this one. But how can we verify that our model is going to work? We can vindicate our model for the theoretical probability with something called the law of large numbers. It states that as the number of trials, in this case die rolls, increases, the observed probability of an event, in this case rolling a 6, will approach a certain value, namely the theoretical probability. Let's use the law of large numbers in our scenario. I simulated 100 die rolls, or approximately 4 games of Candy World, using a random number generator. The x-axis gives the number of die rolls, and the y-axis gives the proportion of 6s I've gotten in that time. You'll notice that the proportion is inching toward 1 out of 6, or about 16.7%, as the number of rolls increases. Given enough die rolls, the dots would all but settle on 1 out of 6. That's ultimately why our model works, and why the theoretical probability of our event is 1 out of 6. So the theoretical probability of an event is really the proportion the law of large numbers settles on for an event in the long run, that is, after many trials. And that's the key. Many trials! And by that I mean, like, a lot. Let's break this down. The odds of rolling a 6 are determined by the law of large numbers, which requires rolling the die many times. Assuming Candy World is a short, half-hour-long game, we won't have many die rolls to work with to approach that 1 out of 6 ratio. It's not hard to imagine that if you roll the die, say, 24 times in a game, you could roll a 6 exactly 4 times, like you'd expect. Or maybe 2 to 3 times, or 5 to 6 times if you're lucky. The die is under no obligation to conform to the theoretical probability in a small number of trials, like we see in Candy World. Which brings us to the second reason the gambler's fallacy is wrong. Independence. Two events A and B are independent if the occurrence of A doesn't affect the probability of B occurring, and vice versa. Independence is one of the most important concepts in all of statistics. Think about 2 die rolls, one after the other. Does one roll at all influence the other? If there's any influence, I certainly can't see it. So does failing to roll a 6 on one die roll, or 2, or 3, or all the die rolls in a game of Candy World make us more or less likely to roll a 6 on the next roll? Alas, no. We have every reason to believe that the rolls of a die are, in fact, independent events. Independence is kind of like that stereotypical guy in a pickup truck you see on the internet ranting about how y'all are too entitled. I'm owed a 6, you say. You ain't owed nothing, says Independence. And he's right. Your odds of rolling a 6 don't improve after a series of low rolls. Instead, your odds of rolling a 6 remain an unchanging 1 out of 6 each time you roll. That's what the law of large numbers says the theoretical probability is. And as long as we're rolling dice, that never changes. So when your friend says, "You're owed a good roll," explain to him that the probability in this context is determined by examining a large number of trials, not just a few, and that consecutive die rolls are independent events, so you're no more likely to roll a 6 than you were before. Or just say nothing at all. That's usually best practice for us nerds. Just whatever you do, don't think like a gambler. Thanks for watching The Math Show with Mr. DeClerico. Be sure to click subscribe, hit the like button, and all that good stuff.